There are planets in this universe that have no sun. They do not orbit a star. They receive no light, no warmth, no gravitational anchor from a parent body. They simply move through the dark, alone, carrying whatever atmosphere or interior heat they still possess, drifting through interstellar space for billions of years. This is Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Tonight, we are going to explore these worlds. We call them rogue planets. Some scientists prefer the term free-floating planets. Others use the phrase orphan planets, a name that carries its own quiet weight. Whatever we call them, they represent one of the more genuinely surprising discoveries in modern astronomy, not because their existence violates any law of physics, but because their numbers, their diversity, and their implications reach further than most people have had occasion to consider. We will look at what rogue planets are and how they differ from the planets we know best. We will explore the two broad pathways by which a planet can end up without a star. We will consider how many of these worlds may exist in our galaxy, and why that number is larger than almost anyone anticipated. We will look at how astronomers detect objects that emit almost no light. We will think carefully about what these worlds are actually like, from their atmospheres down to their interiors. We will ask whether life could exist on a planet with no sun, and we will find that the answer is more open than our intuitions might suggest. We will consider what rogue planets mean for our own solar system, both in terms of its past and its future. And we will end, as we often do on this channel, by simply sitting with the scale of what we have been exploring, letting the ideas settle at whatever pace feels natural. This is a long journey through a quiet subject, and we will take our time with it. Get comfortable. There is no hurry here. Chapter 1. What is a rogue planet? To understand what a rogue planet is, it helps to first think carefully about what we normally mean when we say the word planet, because the definition is less straightforward than it might appear. In our own solar system, every planet moves in a roughly elliptical path around the Sun. Mercury completes its orbit in about 88 days. Earth takes 365. Neptune, the outermost of the 8 recognized planets, takes nearly 165 years to complete a single orbit. These are very different timescales, but they share the same fundamental structure. Each planet is gravitationally bound to the Sun. Each one returns endlessly to roughly the same region of space it occupied before. The relationship between a planet and its star is, in the traditional picture, a permanent and defining one. That relationship is so central to how we think about planets that for most of the history of astronomy, it was considered inseparable from the definition. A planet was, almost by assumption, a body that orbited a star. The possibility that something could be a planet without orbiting anything was not seriously entertained, not because it was physically impossible, but because there was no observational reason to think it happened in significant numbers. That changed in the 1990s and 2000s as improvements in telescope technology and the development of new detection methods began to reveal objects in star-forming regions and in the field of the galaxy that appeared to be planetary in mass but lacked any associated star. These objects were initially viewed with some uncertainty. Were they planets? Were they failed stars? Were they something in between? The debate over terminology reflected a deeper debate about whether these objects were genuinely related to planets as we understood them, or whether they represented a distinct category that happened to overlap in mass. Over time, the scientific community settled on a working definition that is practical if not perfectly precise. A rogue planet is a planetary mass object generally understood to mean an object below approximately 13 times the mass of Jupiter that moves through space without being gravitationally bound to any star. The 13 Jupiter mass boundary is significant because it corresponds roughly to the minimum mass required for an object to fuse deuterium in its core, a process that defines the lower boundary of brown dwarf classification. Objects below that threshold that are not orbiting a star are generally called rogue planets or free-floating planets, depending on the author and the context. This definition has a practical clarity to it, but it papers over some genuine complexity. The mass boundary between rogue planets and brown dwarfs is not sharp, and the formation histories of objects in this mass range can vary considerably. An object of 5 Jupiter masses that formed within a protoplanetary disk and was subsequently ejected from its solar system has a very different origin story from an object of 5 Jupiter masses that formed through the direct gravitational collapse of a gas cloud fragment in isolation. Both would currently be classified as rogue planets under the working definition. Whether they are truly the same kind of object is a question that planetary scientists and stellar astronomers continue to discuss. For our purposes tonight, we will use the term rogue planet to refer to any planetary mass object moving freely through interstellar space, regardless of how it got there. The diversity of formation histories is part of what makes these objects interesting, and we will return to it in the next chapter. With the definition in hand, let us build a clearer picture of what it actually means for a planet to be without a star. Consider the experience of standing on a planet that orbits a sun. The sun dominates. It is the brightest object in the sky by an enormous margin. It provides the energy that drives weather, that warms the surface, that powers photosynthesis, and the entire biological machinery that depends on it. It defines the direction of up in a loose gravitational sense, not literally, but in the sense that the planet's north and south poles are aligned with its orbital axis, that its seasons are produced by the changing angle of solar radiation, that its entire surface environment is shaped by the relationship with that one central source of light and heat. Remove the sun, and everything changes. On a rogue planet, there is no sun to remove, because there was never one to begin with, or because the one that existed has long since been left behind. The sky is dark at all times. There is no day. There is no solar wind sweeping through the upper atmosphere. There is no tidal deformation of the planet's body from a nearby star's gravitational pull. There is no radiation pressure pushing lightly against the planet's outer layers. The planet exists in a state of gravitational autonomy, subject only to the gentle and diffuse gravitational field of the galaxy as a whole, which nudges it slowly along a trajectory that will carry it through the Milky Way over timescales of hundreds of millions of years. The galaxy's gravitational field does exert a pull on rogue planets, of course. Everything in the galaxy is subject to the overall gravitational potential of the galactic mass distribution, which causes objects to orbit the galactic center on timescales of hundreds of millions of years. A rogue planet is not truly free in the sense of being subject to no gravity at all. It is free in the more limited but still significant sense of being unbound to any individual star. This galactic orbit is very different from a planetary orbit around a star. It is slower, more complex, and subject to perturbations from passing stars, molecular clouds, and the overall large-scale structure of the galaxy. A rogue planet's path through the galaxy is not a simple ellipse. It is a long, complicated trajectory that winds through the galactic disk over geological timescales, sometimes passing through regions of higher stellar density, sometimes moving through the relatively empty spaces between the spiral arms. During such a journey, a rogue planet will occasionally pass within gravitational reach of other stars. Not close enough, in most cases, to be captured into orbit, but close enough for the star's gravity to exert a measurable tug on the planet's trajectory, deflecting it slightly from the path it would otherwise have followed. Over billions of years, the cumulative effect of many such weak interactions shapes the rogue planet's trajectory in ways that make it essentially unpredictable over very long timescales. The concept of a rogue planet having a trajectory at all, a path through space that carries it from one region of the galaxy to another, is one that repays some reflection. These are not objects that are sitting still. They are moving continuously at velocities comparable to the velocities of stars in the galactic disk, typically tens of kilometers per second, relative to the local standard of rest. At those velocities, a rogue planet crosses the distance between the Sun and the nearest star in roughly 40,000 years. It crosses the width of the galaxy in a few billion years. These are timescales that dwarf the entirety of recorded human history, but they are not incomprehensible in the context of the age of the universe. A rogue planet that formed 12 billion years ago has had time to cross the galaxy several times. It may have originated in a region of the galaxy that looks completely different today from how it looked when the planet formed. The stars that were its neighbors at birth have long since died. The molecular cloud from which it emerged has long since dispersed. Only the planet remains, carrying in its interior the chemical signature of those ancient conditions, a time capsule moving slowly through a universe that has transformed around it. It is worth pausing here to appreciate just how different this picture is from the one that dominated astronomy for most of its history. For centuries, the solar system was the only planetary system we knew. Every planet we had ever studied was a planet in orbit around a star. The idea that planets could exist in the spaces between stars, and that they might exist in large numbers, was not part of the mainstream picture of how the galaxy was structured. The discovery and subsequent study of rogue planets has changed that picture in a fundamental way. The galaxy is not simply a collection of stellar systems separated by empty space. The space between the stars is populated. It contains objects. It contains worlds, cold and dark and silent, but worlds nonetheless. The interstellar medium, that tenuous mixture of gas, dust, and radiation that fills the spaces between the stars, shares its volume with an enormous population of planetary bodies that belong to no stellar system and orbit nothing but the galaxy itself. This is one of those discoveries that does not change the physics, but changes the picture. It does not require us to revise any fundamental law of nature. It simply requires us to revise our mental image of what the galaxy looks like, to add to the familiar picture of stars and their planets a vast additional population of unlit, unanchored worlds moving through the dark. There are two broad mechanisms by which a planet can find itself in this situation, and they are different enough that they deserve careful treatment. We will explore both of them in detail in the next chapter. But before we move on, it is worth noting one more aspect of rogue planets that sets them apart from the planets we are most familiar with, and that is their age distribution. The planets in our solar system all formed at roughly the same time, about 4.5 billion years ago, from the same protoplanetary disk around the young sun. They are, in geological terms, contemporaries. The rogue planet population is nothing like this. It has been accumulating since the first stellar systems formed in the early universe, more than 13 billion years ago. The oldest rogue planets in the galaxy are ancient beyond easy comprehension. They formed when the universe was a fraction of its current age, when the chemical composition of the galaxy was different, when the density of stars in the galactic disk was higher, when the universe itself looked and behaved differently from how it does today. These ancient rogue planets carry a different chemical composition from younger ones. The early universe was dominated by hydrogen and helium, with very small amounts of heavier elements. The heavier elements, the carbon, oxygen, silicon, iron, and everything else that makes up the solid surfaces and complex chemistry of planets like Earth, were produced by generations of stars that lived and died after the universe formed. The more ancient a rogue planet, the less of these heavy elements it contains, and the simpler its composition tends to be. A rogue planet that formed 12 billion years ago is therefore a fundamentally different kind of object from a rogue planet that formed 1 billion years ago, not in its basic structure, but in its chemistry. It is a record of the early universe, preserved in planetary form, drifting through a galaxy that has grown enormously richer in chemical complexity since the planet's formation. The full range of rogue planets in the galaxy spans this entire chemical history of the universe, from ancient hydrogen-helium-dominated worlds formed in the early cosmos to younger, chemically rich planets, more similar in composition to those in our own solar system. This diversity is part of what makes the rogue planet population scientifically valuable. They are not just curiosities at the edges of planetary science. They are archives. And there are, as we are about to explore, a very great many of them. Chapter 2. How Rogue Planets Form. In the previous chapter, we touched briefly on the two broad pathways that can produce a rogue planet. Now we will slow down and look at each of those pathways in considerably more detail, because the story of how a planet loses its star, or never has one to begin with, is also a story about the nature of planetary systems in general. It is a story about gravity, about timing, about the difference between order and chaos in systems where many massive objects interact over long periods of time. And it is, in its own quiet way, a story about how much of what exists in the universe is the product of disruption rather than stability. Let us begin with the ejection pathway, because it is the one that most directly connects to the kind of planetary system we know best. When a star forms, it does not form alone. The same molecular cloud that collapses to produce the star also leaves behind a rotating disk of gas and dust, the protoplanetary disk. This disk is the raw material from which planets are built. Over millions of years, tiny particles in the disk collide and stick together through a process called accretion, forming larger and larger bodies in a progression that moves from dust grains to pebbles to boulders to planetesimals to protoplanets and finally to planets. This progression sounds orderly when described in sequence, but it is anything but orderly in practice. The protoplanetary disk is a turbulent environment. Gas flows inward and outward. Gravitational instabilities create dense clumps that can grow rapidly. Small bodies collide not just constructively, merging to form larger ones, but also destructively, shattering into fragments when relative velocities are too high. The overall trend is toward growth, but individual bodies can be set back significantly by destructive collisions, and the geometry of who grows where and how fast is sensitive to conditions in the disk that vary from system to system. In the inner regions of the disk, where temperatures are high because of proximity to the young star, only materials with high melting points can condense and solidify. Metals and silicates form rocky grains that accrete into the building blocks of rocky planets. Volatile compounds like water and carbon dioxide remain in gaseous form and are swept inward or outward by the disk's dynamics. This is why the inner planets of our solar system, Mercury, Venus, Earth, and Mars are rocky worlds with relatively thin atmospheres. The conditions in the inner disk favored the formation of dense, refractory materials. Further out, beyond the frost line, the temperature drops enough for water ice and other volatile compounds to freeze into solid grains. This dramatically increases the amount of solid material available for accretion, because water is among the most abundant molecules in the universe. Planets forming beyond the frost line have access to far more building material, which is why the outer planets in our solar system are so much larger than the inner ones. Jupiter and Saturn accumulated enough solid material quickly enough to gravitationally capture enormous envelopes of hydrogen and helium gas from the surrounding disk, becoming the gas giants we know today. Uranus and Neptune grew more slowly, capturing less gas before the disk dissipated, and ended up as ice giants with thick, volatile-rich mantles surrounding rocky cores. The critical thing to understand about this entire process is that it does not produce a tidy, stable system from the start. The early solar system, whether our own or any other, is a crowded and gravitationally complex environment. Dozens or hundreds of planetary embryos may be forming simultaneously. Their gravitational interactions with one another and with the remaining gas in the disk cause their orbits to shift and evolve continuously. Some embryos merge in giant impacts. Some are pushed into resonant orbits by the gravitational influence of larger neighbors. And some, depending on the geometry and timing of the interactions they experience, receive gravitational kicks that send them onto increasingly eccentric orbits, spiraling outward toward the edge of the system. The mechanism by which a planet receives a large enough kick to escape the system entirely is called a close gravitational encounter, or in some contexts, a gravitational slingshot. When a smaller body passes close to a much larger one, the gravitational interaction between them transfers energy from the larger body to the smaller one. The smaller body accelerates. If the energy transfer is large enough, the smaller body reaches escape velocity and leaves the system permanently. The larger body loses a tiny fraction of its orbital energy in the exchange, a loss so small as to be essentially undetectable in the short term, but potentially significant over many repeated interactions. In a system where a large gas giant is migrating inward through the disk, the potential for these interactions is greatly amplified. A gas giant that moves inward disrupts the orbits of every smaller body it encounters along the way. Some of those bodies are swept into resonances with the giant planet and migrate along with it. Others are scattered onto highly elliptical orbits that take them far from the inner system. And some are ejected entirely, their interaction with the gas giant providing the energy kick they need to exceed the escape velocity of the system. Our own solar system carries the evidence of this kind of upheaval written into its structure in ways that researchers have spent decades trying to interpret. The asteroid belt between Mars and Jupiter is thought to be the remnant of material that never successfully coalesced into a planet, largely because Jupiter's gravitational influence continuously stirred the region, keeping relative velocities too high for constructive accretion to dominate. The total mass of material currently in the asteroid belt is a tiny fraction of what was originally present there. Most of it was either accreted by the growing terrestrial planets or ejected from the inner solar system by gravitational interactions with Jupiter during the early period of planetary migration. The Kuiper belt, the ring of icy bodies beyond Neptune, is similarly thought to have been much more massive in the early solar system than it is today. The current Kuiper belt contains only a small fraction of the solid material that models suggest was originally present in the outer solar system. The rest was scattered by the gravitational influence of the giant planets during the period of planetary rearrangement, some of it moving inward to become the projectiles that produced the late heavy bombardment on the inner planets, and some of it moving outward into the Oort cloud, or escaping the solar system entirely. The theoretical framework that best captures this period of solar system history is known as the Nice model, named after the city in France, where it was developed by a group of researchers in the mid-2000s. The Nice model proposes that Jupiter and Saturn originally formed in orbits closer together than their current positions, and that over time they drifted into a gravitational resonance where Saturn completed 2 orbits for every one of Jupiter's. This resonance destabilized the orbits of the outer ice giants, causing them to scatter outward and interact with the vast population of planetesimals in the outer disk. Neptune and Uranus migrated to their current positions through this process, scattering enormous numbers of smaller bodies as they went. Some versions of the Nice model include a 5th giant planet in the early solar system, an additional ice giant comparable to Uranus or Neptune in mass, that was eventually ejected from the solar system during the period of dynamical instability. In these simulations, having 5 giant planets initially actually produces a better match to the observed structure of the outer solar system than starting with only 4. The 5th planet, in this scenario, was the unlucky one whose gravitational interactions with Jupiter or Saturn resulted in a trajectory that exceeded the solar system's escape velocity. It left the solar system billions of years ago and is now somewhere in interstellar space. A rogue planet formed from the same cloud of gas and dust that produced the Earth, moving through the galaxy on a trajectory that began in what is now our cosmic neighborhood. This hypothetical lost planet has no confirmed existence. The evidence for it is indirect, based on the goodness of fit of simulations, rather than on direct observation. But the possibility is taken seriously by researchers who study the early solar system, and it illustrates an important point. Ejection is not an exotic or unusual outcome for planetary bodies. It is a natural consequence of the gravitational dynamics of planetary system formation, something that probably happens in most or all planetary systems to some degree. The timescale over which ejections occur varies considerably. Some planets may be ejected very early in the system's history, during the first few million years when the protoplanetary disk is still present and gravitational interactions are most intense. Others may be ejected later, during the period of giant planet migration and dynamical instability that can occur hundreds of millions of years after the system forms, and some may be ejected much later still, through slow gravitational processes that gradually destabilize orbits over billions of years. Each of these timescales produces a rogue planet with a slightly different history. An early ejection means the planet may still be relatively warm, having retained more of the heat generated during its formation. A late ejection means the planet has spent most of its existence in the relative warmth of a solar system, orbiting a star, before being cast out into the cold. The internal states and atmospheric compositions of rogue planets with different ejection histories will differ in ways that future telescopes may eventually be able to measure. Now let us turn to the second formation pathway, the one that does not involve ejection at all, because it is in some ways the more philosophically interesting of the two. In the densest and coldest regions of molecular clouds, the vast complexes of gas and dust from which stars are born, the process of gravitational collapse does not always produce objects massive enough to become stars. Molecular clouds are not uniform. They are clumpy, with regions of higher and lower density distributed in complex patterns shaped by turbulence, magnetic fields, and the gravitational influence of nearby objects. When a region of the cloud begins to collapse under its own gravity, the outcome depends on how much mass is contained in the collapsing region and how efficiently that mass can shed the angular momentum and thermal energy that would otherwise resist collapse. In regions where the collapsing mass is large, the result is a star. In regions where the collapsing mass is small but still large enough to produce an object of planetary mass, the result can be a free-floating planetary mass object formed by stellar processes rather than by planetary accretion. These objects are sometimes called sub-brown dwarfs, referring to their position below the brown dwarf mass threshold, or they are described as having formed by turbulent fragmentation of the molecular cloud, reflecting the process by which density fluctuations in a turbulent gas can produce collapsing fragments of various masses. The formation timescale for these directly collapsed objects is different from that of planets formed by accretion. Gravitational collapse is a relatively rapid process once it begins, occurring on timescales of thousands to tens of thousands of years, rather than the millions of years required for accretion to build a planet from dust grains. Directly collapsed rogue planets therefore form quickly and in isolation, without passing through the intermediate stages of planetesimal formation and protoplanetary growth that characterize the accretion pathway. One consequence of this rapid formation is that directly collapsed rogue planets may retain more of the primordial gas from their formation environment than ejected planets do. A planet that forms by accretion within a disk has its atmosphere shaped by the disk chemistry and by the proximity of the parent star. A planet that forms by direct collapse in a molecular cloud accretes gas directly from the cloud, potentially resulting in a different atmospheric composition. These differences may be subtle or significant, depending on the conditions of formation, and they represent one of the ways in which future detailed observations of individual rogue planets might eventually allow us to distinguish between the two formation pathways. The discovery of Jupiter mass, binary objects in the trapezium cluster, which we mentioned in the introduction and will discuss in more detail in a later chapter, provides important evidence for the direct collapse pathway. These paired objects, two planetary mass bodies orbiting each other without any associated star, are difficult to explain through ejection. Ejecting two planets from a single system simultaneously in a way that results in them becoming gravitationally bound to each other would require a very specific and unlikely set of circumstances. It is far more natural to explain them as objects that form together through the fragmentation of a molecular cloud, collapsing as a binary pair in the same way that binary stars form. Their existence therefore provides observational support for the idea that direct collapse is a real and significant formation pathway for free-floating planetary mass objects. Both formation pathways, ejection and direct collapse, are operating continuously throughout the galaxy. Every young stellar system that forms is a potential source of ejected planets. Every molecular cloud that produces stars is also potentially producing free-floating planetary mass objects directly through fragmentation. The two populations are being generated simultaneously and continuously, adding to a total rogue planet population that has been accumulating since the first stellar systems formed more than 13 billion years ago. When we think about the galaxy in these terms, as a place where planetary ejection and direct formation of free-floating worlds are ongoing processes that have been operating for most of cosmic history, the scale of the resulting rogue planet population begins to seem not just plausible, but perhaps inevitable. The question is not really whether rogue planets exist in large numbers. The physics makes that essentially certain. The question is how large those numbers actually are, and what the full diversity of the rogue planet population looks like when we are eventually able to observe it in sufficient detail? Those are questions we will begin to address in the next chapter, where we consider what the observations and models currently tell us about just how many rogue planets are out there. Chapter 3. How many are out there? One of the most striking things about rogue planets is not what they are or how they form, but how many of them there appear to be. When astronomers began to seriously investigate the population of free-floating planetary mass objects in the galaxy, the numbers that emerged from their observations and theoretical models were larger than most people had anticipated. Not larger by a small margin, but potentially larger by an extraordinary one. The universe, it turns out, is considerably more populated with dark and wandering worlds than our star-centered view of the cosmos would suggest. Before we get into those numbers, it is worth pausing to appreciate just how difficult the question is to answer with any precision. Counting rogue planets is fundamentally different from counting stars. Stars announce themselves. They emit light across a broad range of wavelengths, and even the faintest stars are detectable by modern telescopes across distances of thousands of light years. Stars are, in the most literal sense, visible. Rogue planets are almost the opposite. They do not shine with nuclear energy. They reflect no starlight because there is no nearby star whose light they could reflect. The only radiation they emit at all is the gentle infrared glow of residual heat left over from their formation, and even that fades over time as they cool toward the temperature of the surrounding space. An old rogue planet, one that formed several billion years ago and has been cooling ever since, emits so little radiation that detecting it from any significant distance requires instruments of extraordinary sensitivity. Most of the rogue planets in the galaxy are, for practical purposes, invisible to us with current technology. We cannot point a telescope at the space between the stars and simply count what is there. We must instead use indirect methods, statistical inference, and theoretical modeling to build a picture of the rogue planet population from limited observational data. This means that all current estimates of the rogue planet population carry substantial uncertainties. They are not precise census figures. They are estimates derived from incomplete samples and models that involve assumptions that are themselves uncertain. With that important caveat clearly in mind, let us look at what the available evidence actually suggests. The first systematic attempt to estimate the rogue planet population through direct observation came from gravitational microlensing surveys conducted in the early 2000s. The principle behind these surveys is elegant, and we will examine the detection method in full detail in the next chapter. For now, it is enough to understand that microlensing surveys can detect massive objects passing between the observer and a background star by the characteristic brightening of the background star's light that results from gravitational lensing. The duration and shape of the brightening event contains information about the mass of the lensing object. Short events correspond to low-mass lensing objects, including objects in the planetary mass range. A major microlensing survey conducted by the Microlensing Observations in Astrophysics collaboration, using telescopes in New Zealand and Chile, and monitoring tens of millions of stars in the direction of the galactic center, detected a population of short-duration lensing events that were consistent with free-floating Jupiter mass objects. Crucially, the number of these events was significantly higher than could be explained by known populations of brown dwarfs and other compact objects. The excess was consistent with a substantial population of free-floating planetary mass objects distributed throughout the galaxy. When the researchers analyzed their data and attempted to translate the number of detected events into a population estimate, they arrived at a figure that was striking in its implications. Their analysis suggested that there could be roughly twice as many Jupiter-mass free-floating objects in the Milky Way as there are stars. Given that the Milky Way contains somewhere between 200 and 400 billion stars, depending on how they are counted, this implies a population of free-floating Jupiter-mass objects in the range of 400 to 800 billion. Those numbers are worth sitting with for a moment. 400 to 800 billion worlds, each roughly the size of Jupiter, drifting through interstellar space without any star to orbit. No sunlight, no seasons, no day, just the permanent darkness of the space between the stars, and within that darkness, an enormous population of cold and wandering worlds. It is important to note that these early estimates carried large statistical uncertainties, and subsequent work has both refined and complicated the picture. Some later analyses of the same and similar datasets suggested that the population of Jupiter-mass rogue planets might be somewhat smaller than the initial estimates indicated, while others suggested it might be larger. The uncertainty reflects the genuine difficulty of the measurement. Microlensing events are rare, the survey data is complex, and translating a count of lensing events into a population estimate requires assumptions about the distribution and velocities of rogue planets in the galaxy that are not independently well constrained. What remained clear through all of this refinement was that the population of free-floating planetary mass objects in the galaxy is large. Whether the true number is 200 billion or 800 billion Jupiter mass rogue planets, the qualitative conclusion is the same. These objects are common. They are not rare exceptions or exotic anomalies. They are a significant component of the galaxy's total inventory of planetary bodies. The picture became considerably more interesting with the recognition that Jupiter mass objects may not even be the most common type of rogue planet. Smaller objects, those with masses comparable to Neptune, Earth, or even smaller rocky bodies, are harder to detect through microlensing because their lensing events are shorter and fainter. Early surveys were not sensitive enough to reliably detect these lower mass events. But as survey technology improved, and as researchers developed more sophisticated analysis techniques, evidence for lower mass free-floating objects began to accumulate. The Korea Microlensing Telescope Network, a dedicated array of 3 telescopes located in Chile, South Africa, and Australia, was designed specifically to address the limitations of earlier microlensing surveys. By observing the same field simultaneously from 3 widely separated locations on Earth, the network can monitor the galactic bulge with much higher cadence than was previously possible, reducing the chance of missing short-duration events corresponding to low-mass lensing objects. Data from this network has provided evidence for a population of Earth-mass free-floating objects, and preliminary analyses suggest that these lower-mass rogue planets may be even more numerous than Jupiter-mass ones. This finding is consistent with what we know about planet formation in general. In most planetary systems, small planets form more readily and in greater numbers than large ones. The processes of accretion and ejection that produce rogue planets should therefore produce more small rogue planets than large ones, all else being equal. If Earth-mass rogue planets are more common than Jupiter-mass ones, and if the ratio between them is similar to the ratio of small to large planets in typical planetary systems, the total rogue planet population could be an order of magnitude larger than the Jupiter mass estimates alone would suggest. Some theoretical models, which attempt to predict the rogue planet population from first principles by combining models of planet formation with models of dynamical instability in planetary systems, arrive at estimates of several trillion free-floating planetary mass objects in the Milky Way when all mass ranges are included. Trillion, not billion. These are genuinely large numbers, and they come with correspondingly large uncertainties. But even if the true number is a fraction of the highest theoretical estimates, the conclusion that rogue planets vastly outnumber stars in the galaxy appears robust. The James Webb Space Telescope has added a completely different observational perspective on the rogue planet population, one that is complementary to microlensing surveys in important ways. Where microlensing surveys provide statistical information about the rogue planet population across a wide range of distances and locations in the galaxy, Webb's direct imaging capabilities provide detailed information about individual free-floating objects in specific young star-forming regions. Young star-forming regions are natural laboratories for studying the free-floating planetary mass object population, because the objects there are still warm from their recent formation. A planet or planetary mass object that formed within the last few million years retains enough heat to emit detectable infrared radiation, making it visible to an instrument as sensitive as Webb, even at distances of hundreds of light years. As the object ages and cools, this thermal emission fades, eventually dropping below any practical detection threshold. But in young clusters, the freshly formed population is accessible. Webb's observations of the trapezium cluster in the Orion Nebula, published in 2023, were particularly revealing. The Orion Nebula is one of the nearest and most active star-forming regions to Earth, located about 1,350 light-years away. The trapezium cluster at its heart contains some of the youngest and most massive stars in the region, surrounded by a rich population of lower-mass objects spanning the full range from stars down, through brown dwarfs, and into the planetary mass regime. Webb's observations detected over 100 free-floating objects in the trapezium cluster, with estimated masses below the brown dwarf threshold. Many of these were in the range of 1 to 4 Jupiter masses, well within the planetary mass regime. The spatial distribution of these objects, scattered throughout the cluster, rather than concentrated in any particular region, was consistent with a population of objects that formed within the cluster, rather than being captured from outside it. What made these observations especially surprising was the discovery of approximately 40 paired objects, 2 planetary mass bodies orbiting each other without any associated star. These Jupiter mass binary objects, the jumbos we have mentioned in earlier chapters, had not been predicted by any existing theoretical model of star or planet formation. Their existence raised immediate questions. How do 2 planetary mass objects end up gravitationally bound to each other in the middle of a young star cluster? What formation process produces them? And how common are they in star-forming regions throughout the galaxy? The most plausible explanation currently proposed for jumbos is that they form through the direct gravitational fragmentation of the molecular cloud, collapsing as bound pairs in the same way that binary star systems form. This explanation requires the fragmentation to produce objects at the low end of the planetary mass range, which is theoretically possible but pushes against the limits of current models of how small a gravitationally collapsing fragment can be. Alternative explanations, including the possibility that the 2 objects in each pair were captured into a mutual orbit after forming separately, face their own theoretical challenges. The jumbos are a reminder that the rogue planet population is more diverse and more complex than our models currently capture. Every time we have looked at young star-forming regions with improved sensitivity, we have found more free-floating planetary mass objects than we expected, and some of them have been objects that existing models did not predict. This pattern suggests that our current theoretical understanding of how free-floating planetary mass objects form and how common they are is still incomplete. Looking ahead, the Nancy Grace Roman Space Telescope represents the most significant near-term advance in our ability to census the rogue planet population. Roman, which is designed to conduct wide-field surveys of the sky in the near-infrared, will carry out a dedicated microlensing survey of the galactic bulge that will dwarf all previous surveys in both scale and sensitivity. Where previous microlensing surveys detected hundreds of planetary mass lensing events over periods of years, Roman is projected to detect thousands or tens of thousands of such events over its mission lifetime, including events corresponding to objects as small as Mars in mass. This dramatic improvement in sample size will reduce the statistical uncertainties in rogue planet population estimates by orders of magnitude. It will allow researchers to characterize the mass distribution of the rogue planet population with much greater precision, distinguishing between different theoretical models of planet formation and ejection. And it will provide the first reliable statistics on the population of Earth mass and sub-Earth mass free-floating objects, a population that we currently know almost nothing about observationally. The Vera Rubin Observatory, a ground-based wide-field survey telescope in Chile that began operations in the mid-2020s, will contribute to rogue planet searches in a different way. Its 10-year legacy survey of space and time will monitor billions of objects in the southern sky, repeatedly over a decade, building up a dataset of extraordinary depth and breadth. While Rubin is not optimized for microlensing surveys, it may detect rogue planets that pass close enough to the Sun to be faintly illuminated by solar radiation, and it will certainly contribute to the broader understanding of the population of solar system and near solar system objects that overlaps with the rogue planet census. Together, these current and upcoming observational programs are transforming rogue planet science from a field dominated by theoretical models and small statistical samples into one with a substantial and growing empirical foundation. Within the next decade or two, we will likely have population estimates for rogue planets that are reliable to within a factor of a few, rather than the order of magnitude uncertainties we currently live with. We will have better constraints on the mass distribution, the spatial distribution within the galaxy, and the relative contributions of ejection and direct formation to the total population. What we will not have, at least not soon, is the ability to study individual rogue planets in the detail that we can study planets in our own solar system or even some exoplanets orbiting nearby stars. The closest rogue planets are still far too distant and far too faint for current technology to resolve their surfaces, probe their atmospheres, or characterize their interiors directly. That level of understanding remains a future goal, dependent on telescope technologies that do not yet exist. For now, the picture that emerges from existing observations and models is one of a galaxy profoundly populated with dark wandering worlds. The spaces between the stars, which we are accustomed to thinking of as essentially empty, are in reality threaded through with an enormous population of cold, silent planets. They are invisible to us in any direct sense. We detect their presence only through the brief distortions they produce in the light of distant stars, or through the faint infrared glow of the youngest among them. But they are there, in numbers that likely exceed the total count of stars in the galaxy by a significant margin. The universe has, it appears, been generating worlds far more prolifically than it has been generating suns to warm them. That is a remarkable thing to know, even approximately. It changes the texture of the darkness between the stars. It populates the void, not with light, but with matter, with worlds, with the quiet, patient, lightless objects that we are only now beginning to learn how to find. Chapter 4. How we detect them. The challenge of finding a rogue planet is, in some ways, one of the purest expressions of what makes observational astronomy difficult. Most of what astronomers study emits light in one form or another. Stars burn with nuclear fire and are visible across billions of light years. Galaxies glow with the combined light of hundreds of billions of stars. Gas clouds fluoresce when ionized by nearby radiation, painting the sky with the soft colors of emission nebulae. Even the cosmic microwave background, the faint afterglow of the early universe itself, fills every direction of the sky with a detectable signal if you have the right instruments to receive it. But a rogue planet, particularly an old one that has been cooling in interstellar space for billions of years, is about as close to invisible as a large physical object can be. It does not shine. It does not reflect. It does not pulse or flare or broadcast radio waves. It is simply a cold, dense mass, moving silently through a part of the universe that contains very little else. Detecting it requires either extraordinary sensitivity to the tiny amounts of infrared radiation it still emits, or a completely different approach that does not rely on the planet producing or interacting with light at all. Astronomers have developed both approaches over the past 3 decades, and together they have opened a window onto the rogue planet population that would have seemed entirely out of reach to an earlier generation of researchers. In this chapter, we will look at each of the major detection methods in turn, examining not just how they work, but what they have revealed and what their limitations are. The first approach, and the one that has provided the most statistically significant information about the rogue planet population as a whole, is gravitational microlensing. We have mentioned this technique in passing in earlier chapters. Now let us look at it carefully, because understanding how it works is essential to appreciating both what it has told us and why the resulting population estimates carry the uncertainties that they do. Gravitational microlensing is a direct observational consequence of general relativity. Albert Einstein's theory of gravity, published in its complete form in 1915. General relativity describes gravity not as a force acting between masses at a distance, as Newton conceived it, but as a curvature of space-time produced by the presence of mass and energy. In this framework, light does not travel in straight lines through a fixed and flat space. It follows the curves of space-time, which means that it bends when it passes through regions where space-time is significantly curved by the presence of a massive object. Einstein himself calculated that light passing close to the Sun should be deflected by a small but measurable angle, a prediction that was confirmed by Arthur Eddington's famous observations during the solar eclipse of 1919. This bending of light by gravity is now a well-established and precisely measured phenomenon. It is observed in many astronomical contexts, from the slight deflection of starlight passing near the Sun to the dramatic distortion of distant galaxies into arcs and rings by the gravity of massive galaxy clusters in the foreground. Gravitational microlensing is the version of this effect that operates on stellar and substellar scales. When a massive object, a star, a brown dwarf, or a planet, passes close to the line of sight between the observer and a more distant background star, the foreground object's gravity bends the light from the background star around it. This bending has a focusing effect, gathering light that would otherwise have traveled past the observer on both sides of the foreground object and directing it toward the observer instead. The result is that the background star appears temporarily brighter than it normally would. The brightening follows a characteristic mathematical pattern over time, known as a Pogzinski curve, after the astrophysicist Bohdan Pogzinski, who first described it in the context of microlensing in the 1980s. The brightness increases smoothly as the foreground object approaches the line of sight, reaches a peak at closest alignment, and then decreases symmetrically as the foreground object moves away. The symmetry and the smooth mathematical form of the curve are what distinguish a microlensing event from other causes of stellar brightness variation, such as intrinsic stellar pulsation or the partial eclipse of a star by an orbiting companion. The duration of the microlensing event depends on several factors, including the mass of the lensing object, its distance from the observer, and its velocity relative to the line of sight between the observer and the background star. For a given distance and velocity, a more massive lensing object produces a longer event, because the region of significant lensing around a more massive object is larger. For a stellar mass lens, a typical microlensing event might last weeks to months. For a Jupiter mass free-floating planet, a typical event lasts days to a week. For an Earth mass free-floating object, a typical event lasts only hours. And for even smaller objects, the events can be so brief as to be essentially undetectable without extremely high cadence monitoring. This relationship between mass and event duration is what makes microlensing a useful tool for detecting rogue planets. But it also illustrates the central challenge. To detect the short duration events produced by planetary mass lensing objects, you need to be monitoring a large number of background stars continuously and with sufficient frequency to catch events that may last only a few hours. Missing an event because your next observation happened after it was already over is a constant concern. This is why microlensing surveys are designed to monitor fields containing the highest possible density of background stars, which means pointing toward the galactic center and the galactic bulge, the densely packed central region of the Milky Way. From our location in the galaxy, the galactic bulge provides a backdrop of hundreds of millions of stars packed into a relatively small area of sky. Monitoring all of those stars simultaneously for brightness changes gives the survey the best possible chance of catching microlensing events, including the short duration ones produced by planetary mass lensing objects. The optical gravitational lensing experiment, known by its acronym OGLE, and based at the Las Campanas Observatory in Chile, has been one of the longest-running and most productive microlensing surveys. Over more than 2 decades of operation, OGLE has monitored hundreds of millions of stars in the galactic bulge, accumulating a dataset of light curves that has been mined repeatedly for microlensing signals of various kinds. OGLE data has contributed to the detection of hundreds of exoplanets orbiting distant stars through microlensing, and it provided some of the earliest evidence for the population of free-floating planetary mass objects. The Korea Microlensing Telescope Network, KMT-NET, represents a significant advance over earlier single-site surveys. By operating identical telescopes simultaneously at 3 widely separated southern hemisphere sites in Chile, South Africa, and Australia, KMT-NET can monitor the galactic bulge continuously without the gaps in coverage that inevitably affect any single-site survey when weather or daylight interrupts observations. This continuous coverage is particularly important for catching short-duration events. KMT-NET's higher cadence has allowed it to detect a population of very short microlensing events, some lasting only a few hours, that are consistent with free-floating objects of Earth mass or below. The analysis of these very short events is technically demanding. At such short durations, the distinction between a genuine microlensing event and instrumental noise or other astrophysical transients becomes difficult to make with confidence. Each candidate short event requires careful vetting, and the statistical analysis of the population of short events must account for various potential contaminants. Despite these challenges, the accumulating evidence from KMT-net and related surveys strongly supports the existence of a large population of Earth mass and sub-Earth mass free-floating objects in the galaxy, adding to the picture established by earlier surveys of the Jupiter mass population. The Nancy Grace Roman Space Telescope, NASA's next large space observatory after the James Webb Space Telescope, is designed in part specifically to revolutionize microlensing surveys of the galactic bulge. Roman carries a wide-field camera with a field of view roughly 100 times larger than that of the Hubble Space Telescope's cameras, allowing it to monitor an enormous area of the galactic bulge simultaneously, with high cadence and high sensitivity. The Roman microlensing survey is projected to last several years and to detect thousands of microlensing events from free-floating planets, including events from objects as small as Mars. This will provide the first statistically robust census of the rogue planet population across the full range of planetary masses, transforming our understanding of how many rogue planets exist and how their numbers vary with mass. The second major detection approach is direct imaging in the infrared, and it works in a fundamentally different way from microlensing. Rather than detecting the gravitational effect of a rogue planet on the light of a background star, direct imaging attempts to detect the planet itself through the faint infrared radiation it emits from its own internal heat. For this approach to work, the planet must be young enough to still be significantly warmer than the surrounding space. A planet that formed billions of years ago has had time to radiate most of its formation heat away and has cooled to temperatures approaching that of the interstellar medium, which is a few degrees above absolute zero. At those temperatures, the infrared emission is far too faint to detect with any current or near-future telescope at typical interstellar distances. But a planet that formed within the past few million years is still warm, potentially hundreds to thousands of degrees above absolute zero in its interior, with upper atmosphere temperatures warm enough to emit detectable infrared radiation. Young star-forming regions are therefore the natural targets for direct imaging searches for rogue planets. These regions contain populations of recently formed objects spanning the full mass range from massive stars down through brown dwarfs and into the planetary mass regime, all of them still warm from their recent formation. The challenge is to identify the planetary mass objects among all the other objects in the region, which requires both high angular resolution to separate closely spaced objects and high sensitivity to detect the faintest and coolest ones. The Hubble Space Telescope contributed early observations in this area, identifying candidate free-floating objects in several young star-forming regions and providing the first indications that the population was larger than theoretical models had predicted. But Hubble's sensitivity to cool infrared-emitting objects was limited, and its observations were restricted to the warmer and more luminous end of the free-floating object population. The James Webb Space Telescope transformed this situation dramatically. Webb's primary mirror is more than 6 times larger in area than Hubble's, and it is optimized for infrared observations across a wavelength range that is ideally suited to detecting cool objects like young rogue planets. Webb can detect objects far cooler and less luminous than Hubble could, pushing the detectable mass range down toward, and potentially, below the mass of Jupiter in sufficiently young and nearby star-forming regions. The 2023 Webb survey of the Trapezium cluster produced the most detailed and extensive census of free-floating planetary mass objects in any star-forming region to date. With its combination of sensitivity and angular resolution, Webb was able to detect objects that were simply invisible to any previous telescope, including not just the 100-plus free-floating planetary mass objects mentioned in earlier chapters, but also the remarkable population of jumbos that had no theoretical precedent. The survey also detected objects at the boundary between the planetary mass and brown dwarf regimes, with enough precision to begin mapping the mass function of free-floating objects in the cluster, providing observational data that theorists can use to constrain models of formation and ejection. Webb is continuing to observe other young star-forming regions. Each new region provides an independent sample of the free-floating object population under somewhat different conditions of stellar density, age, and chemical composition, allowing researchers to understand how these factors affect the number and properties of rogue planets that form or are ejected in different environments. Preliminary results from observations of other regions suggest that the trapezium cluster is not unusual. Free-floating planetary mass objects appear to be common in young star-forming regions throughout the galaxy. Beyond microlensing and direct imaging, there are several additional detection approaches that are either currently in use or being developed for future application. One of these is astrometry, the precise measurement of the positions and motions of stars. If a rogue planet passes close to a star, its gravitational influence will cause a small but potentially measurable deflection in the star's apparent position on the sky. The Gaia Space Observatory, a European Space Agency mission that has been measuring the positions and motions of more than 1 billion stars with extraordinary precision since 2013, is sensitive to these kinds of subtle gravitational perturbations. Analysis of Gaia data for anomalous stellar motions consistent with the gravitational influence of unseen passing masses is an active area of research, though it has not yet produced confirmed rogue planet detections. Another emerging approach involves searching for the thermal emission of rogue planets in wide-field infrared surveys of the sky. The Wide-Field Infrared Survey Explorer, known as WISE, was a NASA space telescope that surveyed the entire sky in infrared wavelengths between 2009 and 2011, and has since been repurposed and operated in a reduced mode. Analysis of WISE data has identified a number of cold objects moving through the solar neighborhood, some of which have been classified as brown dwarfs, and some of which are close to or within the planetary mass range. These nearby cold objects, if they are genuinely free-floating rather than distant brown dwarfs seen in projection, represent some of the most accessible rogue planet candidates for follow-up study. The challenge with wide-field infrared surveys is distinguishing genuinely nearby cold objects from the much larger population of more distant, but intrinsically brighter objects that can appear similar in sky surveys. Measuring the distance to a cold, faint object requires detecting its parallax, the small apparent shift in position that results from observing it from different points in Earth's orbit around the Sun over the course of a year. Detecting parallax for very faint objects requires sensitive observations over a baseline of at least several months, and confirming that a candidate object is genuinely nearby requires multiple independent measurements. This is time-consuming and technically demanding, but it is the necessary step between identifying a candidate rogue planet in a wide-field survey and confirming its nature. Radio astronomy offers yet another potential detection pathway for specific types of rogue planets. Some planets, including Jupiter in our own solar system, produce detectable radio emission through interactions between their magnetic fields and their surrounding plasma environment. A young, magnetically active rogue planet might similarly produce radio emission detectable at interstellar distances with sensitive radio telescopes. The Square Kilometre Array, a major international radio telescope currently under construction in South Africa and Australia, will have the sensitivity to detect this kind of emission from nearby rogue planet candidates, and searches for radio-emitting free-floating planetary mass objects are planned as part of its science program. Each of these detection methods has its own strengths and limitations, and together they provide complementary windows onto a population that no single method could fully characterize on its own. Microlensing provides statistical information about the population over a wide range of distances throughout the galaxy, but tells us very little about the individual properties of detected objects. Direct imaging provides detailed information about individual objects, but is limited to the youngest and warmest members of the population in nearby star-forming regions. Astrometry is sensitive to nearby objects regardless of age, but requires long-time baselines and very precise measurements. Radio detection may eventually allow us to find individual nearby rogue planets through their magnetic activity. The combination of all these approaches, particularly as new capabilities like the Roman Space Telescope and the Square Kilometre Array come online, is gradually building a picture of the rogue planet population that is both broader in statistical scope and richer in individual detail than anything we have had before. We are, in a genuine sense, in the early stages of learning to see a population of objects that was previously almost entirely invisible to us, not because it was not there, but because we had not yet developed the tools to find it. The universe has always contained these worlds. We are only now beginning to learn how to look for them. Chapter 5. What they look like. We have established that rogue planets exist in large numbers, that they form through more than one process, and that detecting them requires considerable ingenuity on the part of astronomers working with instruments that are only now becoming sensitive enough to reveal them in meaningful detail. Now we can turn to a question that is perhaps more immediately evocative, and one that tends to arise naturally when people first encounter the idea of rogue planets. What are these worlds actually like? If we could somehow travel to one and observe it at close range, what would we find? The honest answer is that we do not know with certainty, because no rogue planet has yet been studied with the resolution and sensitivity that would allow us to describe its surface or atmosphere in the kind of detail we can manage for planets in our own solar system. We cannot yet see the cloud patterns of a rogue gas giant, or map the ice fields of a rogue rocky world. Our observational data on individual rogue planet candidates is still sparse, consisting in most cases of a few measurements of infrared brightness and color that constrain temperature and mass estimates, but reveal little about structure or composition. But we are not entirely without guidance. The laws of physics apply equally everywhere in the universe. A gas giant planet moving freely through interstellar space obeys the same equations of fluid dynamics, thermodynamics, and atmospheric chemistry as a gas giant orbiting a star. The differences between a rogue planet and a star-orbiting planet of the same mass and composition are differences of environment, not of physical law. We can therefore use our knowledge of planetary physics, combined with what limited observational data we have on specific rogue planet candidates, to build a reasonably informed picture of what these worlds are like. Let us begin with size and mass, because the range is genuinely enormous. At the upper end of the planetary mass range, just below the boundary with brown dwarfs at around 13 Jupiter masses, rogue planets are enormous objects by any measure we normally apply to planets. Jupiter itself is so large that more than 1,300 Earths could fit within its volume. An object with 10 times Jupiter's mass would be correspondingly larger in volume, though the relationship between mass and radius for gas giants is not linear. Gas giant planets and brown dwarfs of increasing mass actually become progressively denser and more compact as gravity compresses their interiors more efficiently. So the very most massive rogue planets are not dramatically larger in physical size than Jupiter itself, even though they contain far more mass. The most massive rogue planets are therefore not so much larger as they are denser and more internally energetic than Jupiter. At the lower end of the mass range, rogue planets can be comparable to Earth, Mars, or even smaller rocky bodies. These low-massy, rogue planets are far harder to detect through current methods, and far less is known about them observationally. But there is no physical reason why rocky, terrestrial-sized worlds could not exist as free-floating objects. A rocky planet ejected from its solar system carries the same composition it had when it was orbiting its star. Its silicate mantle, its iron core, its geological history, the craters and mountain ranges and ancient lava plains on its surface, none of these are affected by the fact that the planet is no longer gravitationally bound to a sun. It takes them with it into interstellar space, preserved in the cold and darkness, geologically frozen, once its internal heat has dissipated. Between these extremes, there is a rich diversity of possible rogue planet types. Ice giants, objects similar in composition to Neptune or Uranus, with thick mantles of water, ammonia, and methane ices surrounding a rocky core, can exist as rogue planets. Super-Earths, rocky planets more massive than Earth but smaller than Neptune, can exist as rogue planets. Ocean worlds, planets with deep global oceans, can exist as rogue planets, though their surfaces would be frozen solid in the absence of any external heat source. The full diversity of planetary types that we observe in surveys of exoplanets orbiting other stars is almost certainly represented in the rogue planet population, because all of those types can in principle be ejected from their home systems or formed directly in molecular cloud fragmentation. With this range of sizes and types in mind, let us think in more detail about what specific categories of rogue planets are actually like. For a large gas giant rogue planet, the most immediate and physically defining characteristic is the cold. A gas giant orbiting a star receives a continuous input of radiation from its star, which warms its upper atmosphere and drives some of the large-scale weather patterns we observe. Jupiter's upper clouds, for instance, are maintained partly by solar heating, even though Jupiter is predominantly powered from within. A rogue gas giant has no such external energy source. Its upper atmosphere is heated only by the flux of thermal energy escaping from the planet's interior, and by the cosmic microwave background radiation, which contributes a temperature of approximately 2.73 degrees above absolute zero to any object in the universe, an amount so small as to be effectively negligible. The result is that the upper atmospheres of old rogue gas giants are extraordinarily cold. How cold depends on the planet's mass and age. A young rogue gas giant, one that formed or was ejected within the last 100 million years, still retains significant internal heat and may have upper atmosphere temperatures of several hundred degrees above absolute zero, warm enough to maintain a dynamic atmosphere with active cloud formation and atmospheric circulation. An old rogue gas giant, one that has been cooling for several billion years, may have upper atmosphere temperatures close to the temperature of the cosmic microwave background, somewhere in the range of a few tens of degrees above absolute zero at most. At these very low temperatures, the atmospheric chemistry of a gas giant changes dramatically from what we observe on Jupiter or Saturn. Ammonia, which forms the familiar yellow-white cloud bands visible on Jupiter, freezes out entirely at temperatures below about 145 Kelvin, well above the temperatures expected for old rogue gas giants. Methane, which is present in Jupiter's atmosphere in trace amounts, becomes increasingly important as a spectral indicator at lower temperatures, as it does in the atmospheres of the coldest known brown dwarfs. At the very coldest temperatures, water ice clouds may form in the upper atmosphere, giving the planet a pale, frosted appearance quite different from the colourful banding of Jupiter. The internal structure of a rogue gas giant remains similar to that of a star-orbiting gas giant of the same mass and age. Deep beneath the cold upper atmosphere, pressure increases rapidly with depth. Within Jupiter, hydrogen is compressed to such high pressures that it transitions from a molecular gas to a liquid, and at still greater depths to a metallic state in which electrons flow freely through the hydrogen fluid, conducting electricity and contributing to the planet's magnetic field. A rogue gas giant of Jupiter's mass would have the same layered internal structure. A cold upper atmosphere grading into warmer, deeper layers, a transition to liquid hydrogen, a region of metallic hydrogen, and possibly a rocky or icy core at the center. The magnetic field of a rogue gas giant is another aspect of its character worth considering. Jupiter has a magnetic field roughly 20 times stronger than Earth's, generated by convective motions in its metallic hydrogen interior. A rogue Jupiter mass planet would similarly generate a magnetic field through internal convection, though the strength and structure of the field would depend on the planet's rotation rate and the details of its internal dynamics. This magnetic field would create a magnetosphere around the planet, a region of space dominated by the planet's magnetic influence rather than by the interstellar magnetic field. In the absence of a stellar wind, the magnetosphere of a rogue gas giant would be shaped primarily by its interaction with the interstellar medium, the tenuous gas that fills the space between the stars. The interaction between a rogue planet's magnetosphere and the interstellar medium is a relatively unexplored area of planetary physics. On planets orbiting stars, the magnetosphere is constantly compressed and shaped by the pressure of the stellar wind, the continuous outflow of charged particles from the star. A rogue planet has no stellar wind to contend with. Its magnetosphere expands freely until it reaches pressure balance with the interstellar medium, which at typical interstellar densities might occur at very large distances from the planet. In the outer regions of this magnetosphere, charged particles from the interstellar medium are deflected by the planet's magnetic field, creating subtle signatures that in principle could be detected by sensitive radio telescopes, as we noted in the previous chapter. Now let us consider what it would actually be like to approach a rogue gas giant, making the journey in our imagination, since no physical journey to such an object is possible with any technology we can currently envision. You would begin your approach from a great distance, moving through interstellar space toward a position that you knew the planet occupied based on calculations of its trajectory. For most of the journey, the planet would be invisible. The stars would be arrayed around you in their familiar patterns, and the planet would be somewhere among them, indistinguishable from the surrounding darkness at any wavelength your eyes could detect. Only with sensitive infrared instruments would you be able to pick out its faint thermal glow as a point of slightly elevated infrared brightness against the cold backdrop of space. As you drew closer, within perhaps the distance at which Saturn orbits the Sun, the planet would begin to resolve from a point source into a measurable disk in your infrared detectors. Its thermal emission would be centered in the mid-infrared wavelengths corresponding to its surface temperature, and the spectrum of that emission would carry the signatures of its atmospheric composition, absorption features from methane, water vapor if present, and other molecules that absorb or emit at specific wavelengths. From this spectrum, a skilled planetary scientist could estimate the planet's temperature, atmospheric composition, and age with reasonable confidence. Closer still, within perhaps the distance at which Jupiter orbits the Sun, the planet would become visible even to unaided human eyes, under the right conditions, a faint reddish-orange disk glowing with the deep infrared warmth of its own internal heat, assuming it was young enough to still be significantly warm. Its atmosphere would show structure at this range, broad banding from large-scale circulation patterns, perhaps a dark oval storm system reminiscent of Jupiter's Great Red Spot, but colder and slower, visible in the infrared, even though completely invisible to eyes sensitive only to optical light. The sky viewed from within the planet's magnetosphere would be filled with auroral displays in the upper atmosphere, not driven by a stellar wind as on Earth, but by the acceleration of interstellar particles in the planet's magnetic field, manifesting as faint curtains and arcs of light in wavelengths extending from the ultraviolet, down through the visible and into the infrared. These auroras would be the planet's only self-generated light visible at optical wavelengths, a faint shimmer around the poles of a world that otherwise exists in complete darkness. Descending into the upper atmosphere, you would enter a realm of extreme cold and complete darkness at optical wavelengths. Clouds of water ice or frozen methane clathrate would surround you, lit only by the faint glow from deeper atmospheric layers below. The wind would be present, driven by temperature differences between the warm interior and the cold upper atmosphere, but without solar heating to drive the large-scale differential heating that powers Jupiter's jet streams. The circulation patterns might be different, more uniform, less differentiated between the equatorial and polar regions. Deeper still, as pressure and temperature increased, the atmosphere would warm toward the planet's interior temperature, and the chemistry would change. The exotic high-pressure chemistry of deep gas giant atmospheres, where molecules are compressed and transformed into forms that have no analogues in any laboratory environment on Earth, would be fully present regardless of whether the planet orbited a star or drifted alone through space. The internal physics of a gas giant is driven by the planet's own gravitational energy, not by external radiation, and it proceeds independently of the stellar environment. Now let us shift our attention to rocky rogue planets, which present a very different picture. A rocky rogue planet is in many ways the starkest version of a world that exists in the imagination. It is a solid object with a definable surface, moving through interstellar space in complete darkness and extreme cold. Its surface temperature, in the absence of any internal heat reaching the surface and any external radiation from a nearby star, would approach the temperature of the cosmic microwave background, within a few degrees of absolute zero. Nothing on Earth, not the most remote Antarctic plateau, not the deepest oceanic trench, approaches this kind of cold. At such temperatures, every volatile compound that exists on the surface freezes solid. Water, which is liquid on Earth's surface because of the warmth provided by the sun and the insulating effect of the atmosphere, would freeze into water ice almost immediately after a rocky planet was ejected from its solar system and began its journey into the cold of interstellar space. Carbon dioxide, which forms dry ice at temperatures around -78 degrees Celsius, would freeze as well. Nitrogen, the main component of Earth's atmosphere, freezes at -196 degrees Celsius, At the temperatures of deep interstellar space, even nitrogen and oxygen would condense as thin films on the planet's surface. The result would be a world whose surface was covered in a thin but pervasive layer of frozen gases, ice of various compositions coating whatever solid rock or earlier ice lay beneath. In appearance, the surface might bear some resemblance to the surfaces of trans-Neptunian objects in our own solar system, bodies like Pluto or Eris or Sedna that exist far from the Sun and whose surfaces are coated with frozen nitrogen, methane, and carbon monoxide ices. But a rogue rocky planet would be colder still than these objects, which at least receive a trickle of solar energy at their enormous distances from the Sun. Geologically, an old rocky rogue planet would likely be quiet. Tectonic and volcanic activity on a rocky planet depends on the planet having a warm enough interior to drive convection in the mantle, and on sufficient temperature difference between the interior and the surface to keep that convection going over geological time. As a rocky planet cools, its interior solidifies progressively from the outside inward, and tectonic activity slows and eventually ceases. For an Earth-sized rogue planet that has been cooling for several billion years, tectonic activity may have largely ceased, leaving behind a geologically frozen surface that records the history of its active period in ancient mountain ranges and lava plains now preserved under a layer of interstellar frost. But the surface is not the whole story of a rocky rogue planet, and in some ways, it is not even the most interesting part. The interior of a rocky planet is a different environment from the surface, and it operates on different timescales and according to different physical processes. As we noted in the previous chapter, rocky planets generate internal heat through the radioactive decay of long-lived isotopes of uranium, thorium, and potassium incorporated into their interiors during formation. This radiogenic heating operates independently of any external heat source. It does not care whether the planet is orbiting a star or drifting through interstellar space. It simply produces heat at a rate determined by the planet's composition and the half-lives of the relevant isotopes. For an Earth-sized planet with Earth-like composition, the current rate of radiogenic heating is sufficient to maintain the deep interior at temperatures of thousands of degrees, far above the melting point of rock. Earth's mantle is not liquid, because the high pressure at depth raises the melting point of rock significantly, keeping it solid even at high temperatures. But the iron core is liquid in its outer regions, and it is the convective motions of this liquid iron that generate Earth's magnetic field. A rogue rocky planet of similar mass and composition would have similar internal conditions, at least in its youth. Over time, as the radioactive isotopes decay and the interior cools, the liquid outer core would solidify and the magnetic field would weaken. But this process takes billions of years for an Earth-sized body. At intermediate depths, between the frozen surface and the warm interior, there exists the possibility of a liquid layer. If the temperature gradient between the cold surface and the warm interior passes through the melting point of water at some depth, and if water is present in sufficient quantities, a liquid water layer could exist at that depth, insulated from the cold of space by the frozen crust above it, and warmed from below by the planet's internal heat. This subsurface liquid water environment is not merely a theoretical speculation. It is the same principle that maintains the oceans of Europa and Enceladus in our own solar system, and it may operate on rocky rogue planets as well. The sky seen from the surface of a rocky rogue planet would be, in one respect, extraordinary. With no atmosphere dense enough to scatter light, and no nearby sun to create a bright sky background, Every star in the galaxy would be visible from the surface on its own terms, each one a sharp point of light unblurred by atmospheric turbulence. The Milky Way would arch across the sky as a dense, complex river of light, far more vivid and detailed than it appears from Earth's surface through the scattering haze of our atmosphere. Distant galaxies would be visible to the naked eye in greater numbers than they ever are from any location on Earth. The view would be, in a purely astronomical sense, among the finest in the galaxy, but it would be a view in permanent night. No sun would move across that sky. No dawn would lighten the horizon. No warmth would follow from the light of those distant stars, each one too far away to provide any meaningful energy to the frozen surface below. The stars would shine, as they always do, in complete indifference to the cold world beneath them. And that cold world would continue, as it always has, moving through the dark. Chapter 6. Could life exist on a rogue planet? The question of whether life could exist on a rogue planet is one of the more genuinely open questions in modern astrobiology. It sits at the intersection of planetary science, chemistry, biology, and our still incomplete understanding of what life actually requires at its most fundamental level. For most of the history of thinking about life beyond Earth, the working assumption was straightforward. Life needed a star. The energy input from a sun was considered a prerequisite so basic that it was barely worth stating explicitly. A planet without a star was, on this view, simply too cold, too dark, and too energetically impoverished to support the chemical complexity that life requires. That assumption has been eroding for several decades, and the erosion has come not from speculation about distant worlds, but from observations of life on our own planet, in places that were once considered hostile beyond the possibility of biology. The key insight began at the bottom of our own oceans. In 1977, a team of researchers from the Woods Hole Oceanographic Institution, working aboard the deep-sea submersible Alvin, descended to the seafloor near the Galapagos Islands at a depth of about 2,500 meters. They were investigating a region where geophysical surveys had suggested the presence of hydrothermal venting, places where seawater percolates down through cracks in the ocean floor, is heated by the magma beneath, and returns to the seafloor laden with dissolved minerals and chemicals. The researchers expected to find some interesting geology. What they found instead genuinely surprised them. Clustered around the hydrothermal vents, in complete and permanent darkness, at pressures that would crush an unprotected human body, and at distances from the sea surface that no photosynthetically produced organic matter could meaningfully reach, they found thriving ecosystems, tube worms more than a meter long, fields of clams and mussels, crabs, shrimp, fish, and a rich community of microbial life forming thick mats on the rocks around the vents. These were not marginal or struggling communities. They were dense, diverse, and clearly well established, suggesting they had been present for a very long time. The energy source for these ecosystems was chemosynthesis, rather than photosynthesis. Certain species of bacteria living around the vents are capable of extracting chemical energy from the oxidation of hydrogen sulfide, a compound that emerges from the vents in significant quantities along with other reduced sulfur compounds. These bacteria form the base of the food chain, analogously to the role that photosynthetic plants and algae play at the surface. The entire ecosystem, from the bacteria to the tube worms to the fish that feed on them, runs on the chemical energy of the Earth's interior rather than the radiant energy of the sun. This discovery was genuinely transformative for how scientists think about the conditions required for life. It demonstrated that photosynthesis, the process that powers virtually all life on Earth's surface, is not the only viable energy harvesting strategy for biology. It demonstrated that liquid water and chemical energy can support complex ecosystems independently of any sunlight. And it raised the immediate question of whether similar environments, liquid water plus chemical energy without sunlight, might exist elsewhere in the solar system and beyond. In the decades since that first discovery, hydrothermal vent ecosystems have been found in many locations on Earth's seafloor, and the organisms living around them have proven to be extraordinarily diverse and biochemically inventive. Some vent organisms live at temperatures above the boiling point of water at sea level, surviving only because the high pressure at the sea floor raises the boiling point high enough to allow liquid water to exist at temperatures of more than 120 degrees Celsius. Others live in conditions of extreme acidity or alkalinity that would destroy most biochemistry we know. The range of conditions that life has colonized around hydrothermal vents has expanded considerably beyond what the original 1977 discovery suggested, and with each expansion of the known range, the conditions required for life have seemed a little less restrictive. A second key development was the recognition of the full extent of what biologists call the deep biosphere. Beginning in the 1980s and accelerating through the 1990s and 2000s, researchers drilling deep into the ocean floor and into continental rock discovered living microorganisms at depths of hundreds and eventually thousands of meters below the surface. These organisms live in the pore spaces of rock, in conditions of high pressure, complete darkness, and extremely low nutrient availability. Their metabolisms are slow, their generation times can be thousands of years, and they are essentially invisible to any surface-based survey. But they are alive, and they are present in enormous numbers. Estimates of the total biomass of the deep biosphere, the community of microorganisms living within the solid rock of the Earth's crust, suggest that it may be comparable in total carbon content to all of the life living on the surface and in the oceans combined. If this is even approximately correct, it means that a large fraction of all life on Earth exists in an environment that is effectively independent of the sun, powered by geochemical energy rather than solar radiation, and insulated from surface conditions by kilometers of rock. This has direct implications for rogue planet habitability. If such a large fraction of Earth's biosphere can exist independently of the sun, then the removal of the sun from the equation, which is precisely what happens when a planet is ejected from its solar system, does not automatically destroy that fraction of the biosphere. Organisms living deep in the rock, powered by the chemical energy of water-rock reactions and the heat of radioactive decay, might not notice the transition from a planet orbiting a star to a planet drifting through interstellar space. Their environment, kilometers below the surface, changes very slowly and is effectively buffered from events at the surface. With this empirical foundation established, we can now think more carefully about what a rogue planet would need to provide in order to support life, and whether those requirements can be met. The first requirement is energy. Life requires a continuous input of free energy to maintain the thermodynamic disequilibrium that distinguishes a living system from its surroundings. On Earth's surface, this energy comes primarily from sunlight. In the deep ocean and deep rock, it comes from chemical reactions between reduced compounds and oxidized ones, driven ultimately by the heat of the Earth's interior and the chemical gradients produced by water-rock interactions. A rogue planet without a star can provide this kind of chemical energy through the same mechanisms that operate in Earth's deep biosphere, through the radioactive decay of elements in its interior, and through the chemical reactions between warm rock and water. The rate of radiogenic heating in a rocky planet depends on its composition, specifically on the abundances of uranium-238, uranium-235, thorium-232, and potassium-40 in its interior. These isotopes decay on timescales of hundreds of millions to billions of years, releasing heat continuously throughout the planet's lifetime. For an Earth-sized planet with Earth-like composition, the current rate of radiogenic heating is roughly 47 terawatts, a substantial amount of power distributed through the entire volume of the planet. Even a small fraction of this power, concentrated in a subsurface region where water and rock are in contact, could drive the kind of chemosynthetic reactions that support life in Earth's deep hydrothermal environments. As the planet ages and its radioactive inventory depletes, the rate of radiogenic heating decreases. For Earth, the current rate is roughly half what it was at the time of the planet's formation, and it will continue to decrease as the long-lived isotopes decay away over the next several billion years. For a rogue planet of similar composition and age, the same decline in heating rate applies. An old rogue planet, one that formed 10 billion years ago, would have a much lower radiogenic heating rate than a younger one, and the subsurface environment it could maintain for life would be correspondingly more limited. This introduces an important time dimension to rogue planet habitability. A young, rocky rogue planet, freshly ejected from its solar system, would have both significant radiogenic heating and residual heat from its formation, and from the tidal and impact heating it experienced while still part of a planetary system. The subsurface environment of such a planet might be relatively hospitable for an extended period. An ancient rogue planet, cooling for billions of years, would be a progressively less energetic environment, its potential for supporting life declining gradually as its interior cooled and its chemical gradients flattened. The second requirement is liquid water, or some other polar solvent capable of facilitating the complex chemistry of life. Water is so central to biochemistry as we know it, both as a medium for chemical reactions and as a participant in many of those reactions, that it is difficult to imagine a biology that does not depend on it in some form. The question for rogue planets is whether liquid water can exist beneath the frozen surface in the absence of external heating. We have already established that it can, in principle, through the mechanisms of radiogenic heating and the insulating properties of a thick, icy crust. But the details matter. For liquid water to be present at some depth, the temperature gradient between the surface and the interior must pass through the melting point of water at a depth where the pressure is low enough that the melting point has not been raised too much by the weight of overlying rock and ice. The calculation involves the planet's internal heat flux, the thermal conductivity of the overlying crust, the depth of the ice-rock interface, and the pressure-temperature relationship for water at different depths. Theoretical models of these conditions have been worked out for a range of planetary masses and compositions, and the results are moderately encouraging. For an Earth-mass planet with Earth-like composition, liquid water is expected to persist in the subsurface for several billion years after ejection, sustained by radiogenic heating. For a planet somewhat more massive than Earth, with a higher ratio of radioactive elements in its interior, the subsurface liquid water environment could persist even longer. For a smaller planet, the liquid water zone would cool and freeze more quickly as the interior lost its heat. The 2020 theoretical study we mentioned briefly in the previous chapter examined this question in particular detail for the case of a rogue planet with a thick molecular hydrogen atmosphere. The study found that for a rocky planet with a hydrogen atmosphere roughly 100 times the mass of Earth's current atmosphere, radiogenic heating alone could maintain surface temperatures above the freezing point of water for timescales of several billion years. This is a remarkable finding because it suggests that liquid water does not have to be buried deep in the interior under kilometers of ice. It could, in principle, exist at the surface of a rogue planet, open to the sky, for a geologically significant period of time, provided the planet retains a thick enough hydrogen envelope. Retaining a hydrogen-rich atmosphere over geological time is, admittedly, not straightforward. Hydrogen is the lightest element, and atmospheric hydrogen tends to escape into space over time through a process called atmospheric escape, in which energetic molecules in the upper atmosphere gain enough velocity to exceed the planet's escape velocity and fly off into space. On Earth, the original hydrogen atmosphere has long since been lost through this mechanism, replaced by the nitrogen-oxygen atmosphere produced by biological and geological activity. But for a more massive rocky planet, with a stronger gravitational field, atmospheric escape of hydrogen proceeds more slowly. And for a planet that is very cold, the thermal velocities of atmospheric molecules are lower, further reducing the escape rate. So a massive, cold, rogue, rocky planet that retains a thick hydrogen atmosphere is a physically plausible object, and such a planet might maintain surface liquid water through radiogenic heating alone. Whether such a planet exists anywhere in the galaxy is unknown, but the physical conditions for its existence are within the range of what rocky planet formation can produce. The third requirement for life is a supply of the chemical elements that biochemistry uses as its building blocks. On Earth, the relevant elements are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, along with a range of trace elements used by specific biochemical processes. These elements are all cosmically abundant, produced by stellar nucleosynthesis, and distributed through the galaxy by stellar winds and supernova explosions. Any rocky planet that formed in the chemical environment of the Milky Way over the past few billion years would be expected to contain all of these elements in some form. Ejection from a solar system does not remove or destroy a planet's chemical inventory. The carbon, nitrogen, phosphorus, and sulfur that were incorporated into the planet during its formation remain there, available for whatever chemistry the planet's environment supports. The fourth consideration is time, the origin of life on Earth. A process, called abiogenesis, is not well understood even in general outline. We do not know whether it happened quickly or slowly, whether it required unusual conditions that occurred only once, or whether it can happen readily wherever the right conditions exist, or what the precise sequence of chemical and physical steps was that led from simple molecules to the first self-replicating systems. What we do know is that on Earth, life appeared relatively early in the planet's history, within the first billion years and possibly much sooner. This suggests that, given the right conditions, life can arise within a geologically reasonable time frame. For a rogue planet ejected from its solar system, the question of timing is complicated. If the planet was ejected early in its history, before life had time to arise, then the rogue planet would need to develop life from scratch in its post-ejection environment, relying entirely on the chemosynthetic energy sources available in its subsurface. If the planet was ejected after life had already arisen, then some portion of that life might survive the ejection and continue in the subsurface environment of the rogue planet long afterward. The ejection process itself would be catastrophic for life at the surface. The slow cooling of the planet as it moved away from its star would freeze the oceans and eventually the atmosphere, eliminating the surface environment entirely. But organisms living in the deep rock and around subsurface hydrothermal systems might be insulated from these surface changes. The temperature of the deep biosphere is controlled primarily by internal heat, not by surface conditions, and the transition from a planet with a warm surface to a planet with a frozen surface might change the deep biosphere environment only slowly and marginally, if at all. This scenario, life surviving an ejection event by retreating to or already residing in a deep subsurface environment, is physically plausible. It requires that life be present in the planet's deep biosphere at the time of ejection, which is a condition that would be met for any life-bearing planet with a biology similar to Earth's. It requires that the ejection process not be so violent and rapid as to catastrophically disrupt the deep interior of the planet, which for most ejection mechanisms is not expected to be a concern. Gravitational ejection is a slow process on human timescales, though fast on geological ones, and it does not involve any physical impact or sudden heating that would sterilize the interior. If any rogue planets in the galaxy were ejected from life-bearing systems and retained living organisms in their interiors, then the galaxy contains biological material distributed not just in the stellar systems where life originally arose, but also in the interstellar spaces between them, carried there by the same gravitational dynamics that we have been describing throughout this video. The probability of this having happened somewhere in the galaxy, given the enormous number of stellar systems that have existed over the past 10 billion years and the likely prevalence of life among them, is not trivially small. Whether any such life still exists on any rogue planet today, persisting in a slowly cooling subsurface environment over geological time, is a question we have no current means of answering. We cannot detect the biosignatures of a subsurface biosphere on a rogue planet at interstellar distances with any technology we currently possess or can foresee developing in the near future. The detection of life on a rogue planet, if it ever becomes possible, will require advances in both telescope technology and our understanding of what biosignatures to look for that go far beyond anything currently on the horizon. But the question itself is serious, which is perhaps more than it would have seemed a few decades ago, before the discovery of deep-sea vent ecosystems and the recognition of the deep biosphere established that life can exist in the complete absence of sunlight. The universe is larger and stranger than our intuitions suggest, and the conditions for life appear to be less restrictive than we once assumed. In that context, the question of whether some of the trillions of rogue planets drifting through the galaxy might harbor life, quietly and invisibly, in their dark and slowly cooling interiors, is one of the more genuinely open questions in all of science. We are now approximately 90 minutes into our journey through the science of rogue planets, and it is worth pausing briefly to gather the threads we have followed so far. We began with the definition of a rogue planet and the ways in which the absence of a star fundamentally changes a planet's environment. We explored the two formation pathways, ejection and direct collapse, and why both are expected to be common throughout the galaxy. We looked at the observational evidence for an enormous rogue planet population, potentially numbering in the trillions. We examined the detection methods that have made this population accessible to observation for the first time. We built a picture of what rogue planets are actually like, from the cold atmospheres of gas giants to the frozen surfaces and potentially liquid interiors of rocky worlds. And now we have considered whether life could exist on these dark wandering worlds, finding that the answer is a genuine maybe, rather than a clear no. In the next chapter, we will bring this exploration closer to home, considering what rogue planets mean specifically for our own solar system, and what the history of our corner of the galaxy tells us about the worlds that have been set loose into the dark. Chapter 7: Rogue Planets and Our Own Solar System. Everything we have discussed so far has been about rogue planets in a general galaxy-wide sense. We have talked about populations and statistics, about formation mechanisms and detection methods, about what these worlds are like in the abstract and whether they might support life. The picture that has emerged is one of a galaxy far more populated with dark wandering worlds than our intuitions about the cosmos would naturally suggest. Now we can bring that perspective closer to home. The solar system we inhabit is not separate from the story of rogue planets. It is embedded in it. Our solar system formed in a molecular cloud, surrounded by other forming stellar systems. It went through its own period of gravitational upheaval in its early history, a period during which the seeds of the rogue planet population were actively being sown. It exists today within a galaxy full of rogue planets drifting through the spaces between the stars, some of which have almost certainly passed through our outer solar system at some point during the past 4.5 billion years. And in the far future, our solar system itself may contribute additional members to the rogue planet population as the Sun ages and its gravitational influence on the outer planets gradually weakens. The connection is direct and continuous. Our solar system has always been part of the broader ecology of the galaxy, not an isolated island of order surrounded by emptiness, but a participant in ongoing processes that have been shaping the rogue planet population throughout cosmic history. Let us begin with the past, because it is there that the most direct evidence for our solar system's contribution to the rogue planet population can be found. The early solar system was a considerably more dynamic and violent place than the calm, well-ordered system we observe today. In the first few 100 million years after the Sun formed, the giant planets were not in their current orbits. They formed in a more convex configuration, closer to each other, and in some cases closer to the Sun than they are now, and they subsequently migrated to their present positions through a complex series of gravitational interactions with each other and with the vast population of smaller bodies, planetesimals and protoplanets, that surrounded them in the outer disk. This migration was not a smooth or gradual process. Theoretical models suggest that at some point during the early solar system, the giant planets underwent a period of dynamical instability, a relatively rapid reorganization of their orbits driven by gravitational interactions that cascaded through the system over timescales of millions to tens of millions of years. During this period, the outer solar system was, in a word, chaotic. Orbits crossed. Close encounters between giant planets occurred. The populations of small bodies in the outer disk were stirred and scattered, some moving inward to bombard the terrestrial planets, some moving outward into the Kuiper belt and the Oort cloud, and some being ejected from the solar system entirely. The evidence for this period of upheaval is written into the structure of the solar system in several places. The late heavy bombardment, a period roughly 3.9 billion years ago, during which the surfaces of the inner planets, including Earth and the Moon, were subjected to an elevated rate of large impacts, is thought to be one consequence of the gravitational stirring of the outer solar system during this period. The cratered surfaces of the Moon and Mercury preserve a record of this bombardment that persists to this day, since neither body has geological processes active enough to erase the impact record over billions of years. The Kuiper belt provides another line of evidence. The current Kuiper belt is a ring of icy bodies extending from roughly 30 to 50 astronomical units from the Sun, with a total mass only a small fraction of what theoretical models suggest was originally present in the outer solar system. The missing mass was removed by the gravitational influence of the migrating giant planets, scattered into various destinations. Some of it ended up in the scattered disk, a dynamically excited population of trans-Neptunian objects with highly elliptical orbits. Some ended up in the Oort cloud, the vast spherical shell of cometary bodies at distances of thousands to tens of thousands of astronomical units that forms the outermost boundary of the solar system's gravitational domain. And some was ejected entirely, leaving the solar system on hyperbolic trajectories that carried it into interstellar space. The objects ejected into interstellar space from our early solar system are, technically, rogue bodies. They are not planets, most of them being cometary or asteroid-sized fragments, rather than full planetary bodies. But they are solar system material now drifting through interstellar space, contributed by our solar system to the broader population of interstellar small bodies. They join similar contributions from every other stellar system in the galaxy, forming the background population of interstellar debris from which objects like Oumuamua and Borisov are drawn. The question of whether any full-size planets were ejected from our solar system during the period of dynamical instability is a more significant one, and it is one that researchers have examined seriously over the past 2 decades. As we mentioned in earlier chapters, the NICE model and its variants propose that the current configuration of the giant planets, Jupiter, Saturn, Uranus, and Neptune, emerged from a period of instability that involves significant orbital migration and gravitational scattering. In most versions of the NICE model, the instability produces the current 4-planet outer solar system without requiring the ejection of any full planetary bodies. However, some variants of the model and some alternative theoretical frameworks developed more recently produce better matches to the observed structure of the outer solar system when they include an additional giant planet in the initial configuration, one that is subsequently ejected during the instability period. This hypothetical 5th giant planet has been variously estimated to have a mass comparable to Uranus or Neptune, making it an ice giant rather than a gas giant. In simulations that included its interaction with Jupiter during the instability period results in it being placed on a hyperbolic escape trajectory, leaving the solar system at a velocity sufficient to ensure it never returns. The evidence for this hypothetical ejected planet is entirely indirect. We cannot detect it because it would now be at an enormous distance from the Sun, far beyond any current survey capability. We cannot prove its existence from first principles because the simulations that include it are better matches to observations, but not so dramatically better that they constitute proof. What we can say is that the ejection of a planet from our solar system during its early history is consistent with current observational constraints and is supported by a subset of the theoretical models that best explain the solar system's current structure. If such a planet exists, it is now a rogue planet. It formed in the same gas and dust cloud that produced the Earth. It may have had a composition similar to Uranus or Neptune, with a rocky core surrounded by mantles of water, ammonia, and methane ices, topped by an atmosphere of hydrogen and helium. It was ejected 4 billion or more years ago and has been drifting through interstellar space ever since, moving away from the Sun at some tens of kilometers per second on a trajectory that has carried it tens or hundreds of thousands of astronomical units away. It is cold, dark, and completely undetectable, with any instrument we currently possess. There is something quietly poignant about this possibility. A world formed from the same material as the Earth, perhaps with some of the same chemical complexity, perhaps even with a period of geological activity in its early history, set loose into interstellar space before life had any chance to develop here, and long before any mind existed to note its departure. It has been traveling for 4 billion years through regions of the galaxy that no human being has ever seen or named, carrying in its frozen interior a chemical record of the early solar system that we will almost certainly never be able to read. Closer to the present, there is the question of interstellar objects passing through our solar system, a question that moved from theoretical to observational in 2017, with the detection of the first confirmed interstellar visitor. Oumuamua, officially designated 1I/2017 U1, was discovered in October 2017 by the Pan-STARRS Survey Telescope in Hawaii. Its trajectory through the solar system was immediately recognized as hyperbolic, meaning it was moving far too fast to be gravitationally bound to the Sun. It had come from interstellar space, passed through the inner solar system at high speed, and was already on its way out when it was discovered. By the time sufficient observations had been made to characterize it, it was already receding and could not be studied in detail. Oumuamua was a small object, estimated to be perhaps a few hundred meters in its longest dimension, and its shape and behavior were unusual in ways that generated significant scientific discussion. Its brightness varied dramatically as it rotated, suggesting an elongated or pancake-like shape quite unlike most solar system bodies. It exhibited a small but measurable non-gravitational acceleration as it left the solar system, an acceleration that could not be explained by the gravity of the Sun or the planets. Various explanations were proposed for this acceleration, ranging from outgassing of volatiles to more exotic hypotheses, but no consensus was reached. What Oumuamua demonstrated clearly was that interstellar objects do pass through the solar system. The fact that one was detected within the first few years of survey telescopes capable of finding it suggests that such objects pass through on a relatively frequent basis, perhaps several per year for objects of Oumuamua's size. The detection of Borisov, the second confirmed interstellar object, just 2 years later in 2019, reinforced this conclusion. Borisov was an interstellar comet, showing clear signs of outgassing consistent with a volatile-rich composition, and its trajectory was similarly hyperbolic. These small interstellar objects are not rogue planets. They are fragments, debris from other stellar systems, comparable in size to the smallest bodies in our own solar system. But their detection confirms the broader principle that interstellar space contains objects from other stellar systems, and that some of those objects occasionally pass close enough to the Sun to be detectable. For true rogue planets, the question is whether any pass through our solar system on timescales comparable to its age. Statistical estimates based on the expected density of rogue planets in the solar neighborhood suggest that rogue planets do pass through the outer solar system, beyond the orbit of Neptune, on timescales of millions to hundreds of millions of years. These passages would generally occur at distances of hundreds of astronomical units or more, far enough that their gravitational effect on the planets would be negligible. They would be completely undetectable with current technology, but they would be happening silently and invisibly as a consequence of the rogue planet population that fills the galaxy around us. The probability of a rogue planet passing close enough to the inner solar system to have any significant gravitational effect on Earth or the other inner planets is extremely small on any human timescale. The inner solar system is a small target, and rogue planets move through the outer solar system too quickly to be captured by the Sun's gravity in most cases. The solar system has remained stable for 4.5 billion years, and there is no reason to expect that to change on any timescale relevant to human civilization. There is one hypothetical object, however, that has attracted considerable scientific attention, and that connects the story of rogue planets directly to the current structure of the outer solar system. This is the proposed Planet 9, a hypothetical large planet in the very outer solar system, whose existence has been inferred from the orbital clustering of a population of small trans-Neptunian objects. The hypothesis was proposed in 2016 by astronomers Konstantin Batygin and Mike Brown, based on the observation that a group of small bodies in the outer solar system, each with highly elliptical orbits extending to very large distances from the Sun, have their orbital orientations clustered in a way that is statistically unlikely to be random. The most straightforward explanation for this clustering is the gravitational influence of a large, distant planet, whose gravity has shepherded these smaller objects into their current orbital configuration over billions of years. The proposed Planet 9 is estimated to have a mass of 5 to 10 times Earth's mass, placing it in the super-Earth category, and to orbit the Sun at an average distance of somewhere between 400 and 800 astronomical units, far beyond the most distant known planets. At such a distance, it would be extremely faint and would move very slowly across the sky, making it difficult to detect in any survey that does not specifically target its expected location over an extended period of time. Whether Planet 9 exists remains unconfirmed. No direct detection has been made, despite searches by several teams using various telescopes. Some researchers have questioned the statistical significance of the orbital clustering that motivated the hypothesis, suggesting that it may be partly an artifact of observational biases in how trans-Neptunian objects are discovered. Others maintain that the clustering is real and significant, and that a massive perturber is the most natural explanation for it. If Planet 9 does exist, its origin is an interesting question. It may have formed in the outer solar system and been pushed to its current distant orbit by gravitational interactions with the giant planets during the early period of dynamical instability, stopping just short of ejection. Alternatively, it may be a captured rogue planet, an object that formed in another stellar system, was ejected from that system, and was subsequently captured into a loose orbit around the Sun during a close encounter. Gravitational capture of a rogue planet is an improbable event in general, because it requires the rogue planet to lose enough energy during the encounter to become bound to the Sun, which in turn requires interaction with a third body to carry away the excess energy. But in the early solar system, when the Sun was still part of its birth cluster, surrounded by other young stars, close encounters between stellar systems were more frequent, and capture events, while still rare, were more likely than they are today. The possibility that Planet 9, if it exists, might be a captured rogue planet adds an interesting dimension to the story. It would mean that the outermost member of our solar system is not native to it, that it formed around another star in another part of the galaxy, was ejected from that system at some point in the past, and ended up in a loose orbit around the Sun through a chance gravitational interaction. It would be an ambassador from another stellar system, carrying in its composition a record of conditions around its parent star that we might one day be able to read. Whether or not Planet 9 turns out to be real, the broader principle it illustrates is important. The boundary between the solar system and the surrounding interstellar environment is not sharp. Material flows across that boundary in both directions. Our solar system has contributed objects to interstellar space, and interstellar objects occasionally enter our solar system, and in rare cases may be captured by it. The solar system is not a closed container. It is a permeable structure, embedded in a galaxy that contains an enormous population of wandering objects, some of which we are only now beginning to learn to find. Looking further into the future, the Sun itself will change in ways that affect the solar system's gravitational structure. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin to expand into a red giant, swelling to a size that engulfs the inner planets and dramatically alters the conditions throughout the solar system. During this expansion, the Sun will lose mass, carried away by an intensified stellar wind. As the Sun loses mass, its gravitational pull on the outer planets weakens, and their orbits expand outward in response. For the inner planets, the red giant phase is catastrophic. Mercury and Venus will almost certainly be engulfed as the Sun expands. Earth's fate is less certain, sitting close to the boundary of the expanding Sun's surface and potentially surviving, but in a completely sterile and unrecognizable form. Mars and the outer planets will survive the red giant phase, but will find themselves in significantly different orbits as the Sun shrinks down to a white dwarf, a dense stellar remnant with roughly half the Sun's current mass, but the physical size of the Earth. The transition from a star to a white dwarf releases enormous amounts of energy and dramatically reduces the gravitational influence of the central body on the outer solar system. In the white dwarf phase, the Sun's gravity is only half as strong as it is now, because the mass has been reduced by half through the stellar wind losses of the red giant and subsequent evolutionary phases. The orbits of the surviving outer planets, Uranus, Neptune, and any hypothetical distant planets, will shift outward in response to this mass loss. Neptune, already the most loosely bound of the major planets, is the most vulnerable to eventual escape. Its orbit in the white dwarf solar system will be substantially larger than it is today, and its gravitational binding to the white dwarf will be correspondingly weaker. A passing star, a close encounter with another object, or the accumulated gravitational influence of repeated interactions with other outer solar system bodies could, over the many billions of years of the white dwarf phase, nudge Neptune onto an escape trajectory. In that scenario, Neptune would depart the solar system, becoming a rogue planet in its own right, carrying its moons and its ring system with it into the interstellar dark. This is a prospect so remote in time that it is essentially meaningless on any human scale. The Sun will not begin its red giant phase for another 5 billion years, and the eventual escape of Neptune, if it happens at all, lies billions of years beyond that. The universe as we know it will be profoundly different by then. The stars visible tonight will have changed. New ones will have formed. The Milky Way will have merged with the Andromeda Galaxy, and the combined galaxy will have evolved into a different structure altogether. Whatever becomes of life and intelligence over those timescales is beyond our ability to even speculate about meaningfully. But the physics is real, and it is a reminder that the solar system is not a permanent arrangement. It is a temporary configuration of matter, held together by the gravity of a star that is itself temporary. The rogue planets drifting through the galaxy today are the former inhabitants of systems like our own, released by the same physical processes that are slowly and imperceptibly reshaping our solar system with every passing million years. We have contributed to the rogue planet population in the past. We may contribute to it again in the future. The solar system and the rogue planet population are not separate stories. They are different chapters of the same ongoing narrative, written in the language of gravity and time, across a canvas so large that no single perspective can take it all in at once. Chapter 8. The Philosophy of Wandering Worlds. We have spent this evening moving through the science of rogue planets with some care and considerable patience. We have looked at what they are and how they differ from the planets we know best. We have explored the mechanisms by which a planet can lose its star, or never have one to begin with. We have considered the extraordinary numbers that the evidence suggests. A galaxy populated not just by stellar systems and their attendant worlds, but by an enormous additional population of free-floating planetary bodies that belong to nothing and orbit nothing but the slow gravitational currents of the Milky Way itself. We have looked at the ingenious methods astronomers use to detect objects that emit almost no light, and at the remarkable findings that those methods have produced. We have thought carefully about what rogue planets are actually like, from the cold upper atmospheres of gas giants to the potentially liquid interiors of rocky worlds insulated from the cold of space by kilometers of frozen crust. We have asked whether life could exist on a planet with no sun, and found that the question deserves to be taken seriously. And we have considered what all of this means for our own solar system, both in terms of the worlds it may have lost in its early history and the worlds it may yet release in its distant future. In this final chapter, we are going to do something different. We are going to slow down even further, below the already deliberate pace we have maintained throughout, and simply sit with some of the broader implications of what we have been exploring. Not to draw tidy conclusions or wrap everything in a satisfying summary, but to allow the ideas to settle at whatever depth they naturally reach when we stop pushing them and simply let them rest. The first thing worth sitting with is the number. Throughout this video, we have mentioned estimates suggesting that rogue planets may outnumber stars in the Milky Way by a significant margin. The most conservative estimates place the rogue planet population at roughly equal to the stellar population, somewhere in the hundreds of billions. The more generous estimates, those that include all planetary mass ranges and both formation pathways, push the number into the trillions. The uncertainties are large, and the true number will not be known with any precision until the Roman Space Telescope and subsequent surveys have had time to conduct the kind of census that current instruments cannot. But even taking the most conservative estimates seriously, the implication is remarkable. The majority of planetary bodies in the Milky Way are not orbiting any star. The majority of worlds are dark. The majority of planets, by raw count, have never experienced a sunrise. They know no seasons driven by the changing geometry of their relationship with a star. They carry no oceans warmed by stellar radiation, no atmospheres photochemically shaped by ultraviolet light, no magnetic field interactions driven by a stellar wind. They exist in a condition of gravitational solitude that is, when we think about it carefully, the default condition of a world that has been set free from the organized structure of a stellar system. We tend to picture the galaxy as a collection of lit and warmed places, islands of light surrounded by darkness, stars and their families of planets, each system a small sphere of relative warmth and photochemical complexity in the cold and chemical simplicity of interstellar space. This picture is not wrong. Stellar systems are real, and the conditions they create are genuinely special in the context of the broader universe. But if the rogue planet estimates are approximately correct, that picture is deeply incomplete. The darkness between the stellar islands is not empty. It is populated, densely by astronomical standards, with worlds that have no connection to any of those islands of light. When we look at the night sky and see the stars arrayed above us, each one a sun potentially surrounded by its own family of orbiting worlds, we are seeing something real and beautiful. But we are also seeing only the luminous minority of the galaxy's worlds. The dark majority is invisible to us, present in every direction we look, drifting through the spaces between the stars that we can see, silent and cold and moving on trajectories that will carry them through the galaxy for billions of years in any direction we care to name. This does not diminish the stars. It simply adds something to the picture that was missing before we developed the tools and the theoretical understanding to know it was there. The second thing worth reflecting on is what rogue planets tell us about the nature of order and its relationship to what we think of as normal. Every planet we studied for the first several centuries of observational astronomy was a planet in orbit around a star. Every exoplanet discovered in the first decades of exoplanet research was a planet orbiting a star. The concept of a planet was so thoroughly fused with the concept of stellar orbit that the two were functionally inseparable in the scientific imagination. A planet was, by assumption and by definition, a body that belonged to a star. The discovery and subsequent characterization of the rogue planet population represents a genuine expansion of what the word planet can mean, not just in a technical, definitional sense, but in a deeper conceptual sense. It tells us that the orderly structure of a stellar system, with its central star and its orbiting family of planets each occupying a stable niche, is not the inevitable outcome of planet formation. It is one outcome among several. Many planets spend their entire existence in orbit around a stable star, but many others are disrupted, displaced, and set loose. The orderliness we observe in our own solar system is real, but it is the result of a particular gravitational history, set of interactions during the early solar system that happened to resolve in a configuration stable enough to persist for 4.5 billion years. Other planetary histories resolve differently. Some produce systems with very different orbital architectures from our own. Some produce planets that were ejected before stability was achieved. Some produced rogue planets directly, without any period of stellar association at all. The diversity of outcomes is enormous, and the ordered solar system we inhabit, while not unique, is far from the only way that the matter of a protoplanetary disk can organize itself. There is something quietly grounding about recognizing this. We live on a world that is, by some measures, fortunate. It orbits a stable star at a distance that permits liquid water at its surface. It is large enough to hold an atmosphere, but not so large as to retain a crushing hydrogen envelope. It is accompanied by a large moon that has stabilized its axial tilt and driven the tidal dynamics that may have contributed to the origin of life. It exists in a solar system whose gravitational architecture has been stable for billions of years, protecting the inner planets from a constant bombardment by cometary material from the outer solar system. None of these favorable circumstances were guaranteed. The gravitational dynamics of the early solar system could have resolved differently. We could have been on a planet that was ejected. We could have been on a world that ended up as a rogue. The fact that we are here, on a lit and warmed world in a stable orbit, is the product of a particular history that included many possible alternatives. This is not a reason for existential anxiety. It is simply an accurate description of the contingency of our situation. We are here because of a long sequence of physical events that happened to turn out as they did. The rogue planets represent the sequences that turned out differently, the worlds that were set loose. rather than settled, that are wandering rather than orbiting, that exist outside the organized structures that we tend to think of as the primary features of a planetary universe. They are not failed planets. They are planets with a different history, moving through a different phase of their existence. The third reflection is about scale, and specifically about the relationship between the scales of rogue planet science and any scale on which human experience normally operates. We have mentioned throughout this video that rogue planets drift through interstellar space on timescales comparable to or exceeding the age of the universe. Some of the oldest rogue planets in the galaxy have been moving for more than 12 billion years. To put that in a context that might make it slightly more tangible, consider the following sequence of durations. A human lifetime is roughly 80 years. The entirety of recorded human history, from the earliest written records to the present day, spans roughly 5,000 years. The time since the extinction of the non-avian dinosaurs is about 66 million years. The age of the Earth is about 4.5 billion years. The age of the universe is about 13.8 billion years. And some rogue planets have been drifting for close to that entire span, formed in the early universe when the first stellar systems came together and began their own long histories. In 12 billion years of travel at typical interstellar velocities, a rogue planet covers a distance of hundreds of thousands of light years. The Milky Way is about 100,000 light years across. An ancient rogue planet has had time to cross the galaxy several times, drifting back and forth through the galactic disk under the slow influence of galactic gravity, passing through regions of higher and lower stellar density, occasionally coming within a few light years of a star before moving on, accumulating in its trajectory a kind of history that no human narrative can adequately capture. What has the galaxy looked like during that journey? When the oldest rogue planets formed, the universe was less than 2 billion years old. The Milky Way itself was younger and more active, with a higher rate of star formation, a more turbulent interstellar medium, and a different distribution of heavy elements than it has today. The spiral arm structure that gives the modern Milky Way its characteristic shape was less developed. The population of old red giant stars that now fills the galactic bulge was not yet present. The chemical evolution of the galaxy, the slow enrichment of the interstellar medium with the heavy elements produced by successive generations of stellar nucleosynthesis, was at an earlier stage. The ancient rogue planets formed in that earlier universe carry a chemical signature of it in their compositions. Their rock, if they have rock, contains different ratios of heavy to light elements than the rock of planets formed more recently. Their iron cores, if they have iron cores, contain a different mix of isotopes than Earth's core does. They are, in the most literal sense, artifacts of an earlier cosmos, preserved in planetary form and carrying their chemical memories through a universe that has transformed around them. This is one of the reasons why a future capability to characterize individual rogue planets in detail, to measure their compositions and internal structures directly, would be scientifically extraordinary. Each rogue planet is a data point in the chemical and dynamical history of the galaxy. The full population of rogue planets, if it could ever be characterized in sufficient detail, would constitute a kind of fossil record of galactic history, written not in rock strata, but in the compositions of worlds drifting through interstellar space. We are nowhere near that capability now. We are still at the stage of learning that these objects exist in large numbers and developing the tools to count them. But the potential scientific value of what lies beyond our current reach is genuinely remarkable. The fourth reflection is about what the existence of rogue planets means for our understanding of what the universe is like as a place. For most of human history, the universe as understood by science was a place of lit and structured things. Atoms, molecules, stars, galaxies, clusters of galaxies, the large-scale web of cosmic structure visible in maps of the distribution of matter across billions of light years. The objects of astronomical study were, almost without exception, objects that could be seen because they emitted or reflected some form of radiation. The existence of objects that were genuinely dark, present in significant numbers but emitting almost nothing detectable, was known in the abstract but not well characterized. Rogue planets are one part of a broader picture of the dark universe that has been gradually coming into focus over the past several decades. Dark matter, the still unidentified material that makes up roughly 27% of the universe's total mass energy content, is a more significant component of this dark universe, invisible by definition and detectable only through its gravitational effects. Dark energy, the mysterious driver of the universe's accelerating expansion, is more mysterious still. Compared to these cosmological puzzles, rogue planets are almost mundane. They are ordinary matter, ordinary physics, ordinary planets. They are dark only in the sense of emitting very little radiation, not in any more exotic sense. But their existence is a reminder that our picture of the universe is always built from the things we can detect, and that the universe contains a great deal that sits just outside the reach of our current instruments and techniques. The history of astronomy is in part a history of discovering what we were not yet able to see, and then developing the tools to see it. The history of rogue planet science is a small chapter in that larger story, one that is still being written. The fifth and final reflection is the simplest, and perhaps the most worth resting with as this video draws toward its close. Somewhere in the galaxy tonight, an old rogue planet is moving through the space between the stars. It has been moving for billions of years. It has no name. It has never been observed by any telescope. It carries no record of having been studied or thought about by any mind in the universe. Its surface is frozen, coated in layers of ice that have been accumulating since it left the warmth of whatever star it once orbited, or since it formed in the dark of a molecular cloud and never knew warmth at all. The stars are visible from its surface in permanent night, the same stars that we see from Earth, arranged in very nearly the same patterns. The Milky Way arches across its sky as it arches across ours, a river of light in a dark sky. Somewhere in its interior, depending on its age and composition, there may still be warmth, a slow radioactive fire, burning at a geological pace, keeping some fraction of the interior above the temperatures at which chemistry becomes impossibly slow. Whether that warmth is enough to maintain liquid water, and whether liquid water is enough to maintain the kind of chemistry that eventually becomes biology, we do not know. We may never know for this particular world. It is one among trillions. The planet does not know any of this. It moves because it has momentum, because nothing has stopped it, because the galaxy's gravity has given it a trajectory, and it is following that trajectory with the perfect, patient indifference of an unconscious physical object. It will continue moving for as long as the universe allows, which is to say for a very long time. There is something in this image that resists resolution into any particular emotional key. It is not melancholy, and it is not inspiring in any conventional sense. It simply is. A world moving through the dark, in a universe that is larger and older and stranger than our ordinary experience gives us any reason to suspect. We live on a different kind of world, a lit and warmed one, orbiting a star in a stable and ordered system that has given us the time and conditions to develop into beings capable of asking questions about what else is out there. We have used that capability to look into the darkness and begin to see the things that were there all along, waiting to be noticed. The rogue planets are among those things. They have been there since the beginning of the galaxy's history. We are only now, at this particular moment in the development of our instruments and our understanding, becoming aware of them in any meaningful way. That awareness is new. The planets are not. They have been moving through the dark for longer than the Earth has existed, and they will continue moving through the dark long after the sun has exhausted its fuel and the solar system has changed beyond recognition. Tonight, some of them are perhaps closer to us than any star, invisible, cold, drifting, and silent.